Disjoint and overlapping are like ways we can describe events the same way in section 10.2 we use the words independent and dependent to describe events. We'll get to our definitions of disjoint and overlapping here in just a moment, but first we want to talk about what are compound events. Now, compound events are different, and this will be the hardest part about probability as we move forward because you'll now have like all different types of probability. How do you tell the difference? Compound events are different than the events we talked about in section 10.2. Remember in section 10.2 our keyword was and I had put a qualifier on your and, like and then. So it meant you do one thing and then you do another thing and then you do another thing. And if you're doing all these different things, then you multiply your probabilities together. Compound events are outcomes that happen at the same time or from the same event. So two outcomes are possible from doing one thing. Examples that you'll often see are like deck of card problems. So what if I reach into the deck and I pull a card from the deck of card? What's the probability that the card is a red card or a spade? So I could pull a card that could be either one of those. Okay, that's different than what we did back in section 10.2. What's the probability I pull a red card and then a spade? Okay, where I'm pulling two cards. Okay, so as you're reading problems on homework, reviews, tests, quizzes, you'll have to be thinking about that. Is this one where I'm doing two things, so I should multiply, or am I really doing one thing and looking at two outcomes from the same event? Then I should be adding. Okay. They will be classified as overlapping or disjoint, so we'll talk about those definitions here in just a minute. And like I said, that's like describing our other events as dependent or independent. And the keyword here is going to be or. Now, I would put somewhere here on your notes, and I'm going to talk about this again, but I did this for section 10.2, and then meant multiply, or means add. A weird thing about the ors is that there's also an and. So that can really get some people because now we're going to have two probabilities that have and in them, but they mean different things. So we're going to really have to like think through problems, read through, contemplate, decide what those things actually mean. Do they mean and then? Or do they mean in this section and at the same time? All right, let's draw a visual of compound events. And I'm going to draw it as a Venn diagram. We're going to have a few Venn diagrams in our notes today. Suppose I have some event A, and I'll also draw some event B. If I were to be discussing the part that is A or B, everything inside of those two circles is part of that answer. So I could be just A, I could be just B, or I could be both. So every part of those circles is part of A or B. the stuff on the outside in my sample space, things that are not included in either one of those circles, those are not A, not B. Okay. Now we're going to talk about the overlapping events. And you could probably tell from that previous slide where the overlapping events were, or what overlapping events look like, where your overlap was. Overlapping events are two events that have one or more outcomes in common. So they have some overlap. That's the same picture. A and B are overlapping events. They share some outcomes in common. Where are those outcomes? In the middle of that Venn diagram. Okay, so I'm going to go ahead and on this, I'm going to mark this middle, this shaded area. A or B is all of the circles, right? Like in the last example. But the part that I'm labeling right now, this is the overlap. It's the part that they share in common. Now that's going to come back to us in our formula, and this is where that extra and comes in. So the overlap means it's A and B at the same time. So this is different than the A and B we were looking at in our previous section, right? It will be really important that you read a problem and try to decide. Does it mean and then when it says and? Or does it mean and at the same time? What would a picture for disjoint events look like if they have no outcomes in common? How would you draw that? Two separate circles, no overlap, right? So disjoint, or another phrase that you should be familiar with, is the word mutually exclusive. Those are things that have no events in common. And we can draw the picture that Lexi described. Here's A. Here's B. No overlap. If I went back to like my overlapping events above where we shaded in all the circles, you know, I could have drawn that picture like this as well, and I would have just shaded all the A and would have shaded all the B. That's A or B together. It doesn't matter which one it is, it's just one of the two. Everything else is not A or B. But in this case, we're talking about the idea of if they have overlap or if they don't have overlap. Okay, so I just want to kind of prep you for what's going to happen later in the chapter when everything gets put together on reviews, quizzes, and tests, right? The first thing I would do when I came to a problem for probability is I would try to read it and decide between and, meaning and then, which I should then multiply probabilities, or, where I should add probabilities. And there's going to be subtraction in there. We'll see that in our formula. Okay. But you'll have to decide between those two versions. Is it two separate events, or is it two outcomes from one event? Once you decide which one of those it is, whether you're going to be multiplying two probabilities or you're going to be adding two probabilities, then you have to decide if you're multiplying, are they independent or dependent? And if you're adding, are they overlapping or disjoint? Okay, so you should be able to do both of those decisions. Okay, now I have my column switched from what is on your sheet, so I don't care how you go about if you want to rename the columns or you just want to make sure you flip-flop them when you write them down. Just be aware I accidentally have them switched. So I'm making sure you're paying attention, I suppose. Okay, in the disjoint or mutually exclusive column, I would write something just like in plain English. What does disjoint or mutually exclusive mean? You cannot be both at the same time. Both meaning the two events or outcomes that we're investigating.
I did right.
And then overlapping would mean you could be both at the same time. There is some overlap that exists. You don't have to be both, but you could be. An example. If we're talking about disjoint or mutually exclusive events, imagine, I think there was a question about marbles on your quiz. Pulling solid colored marbles from a bag is going to be disjoint. What's the probability I pull a green marble or a yellow marble? Well, if I only pull one marble, I'm not going to pull both. Okay. So those would be disjoint or mutually exclusive. Versus that deck of cards, let's say I'm going to reach into the deck and I'm going to pull a single card. What's the probability that it's a black card or a face card? Well, it could be both, right? It could be a jack, queen, king of clubs or a jack, queen, king of spades. Okay. So there are some cards where it could be both. Another example, disjoint or mutually exclusive freshman, sophomore. And I'm speaking specifically here to the number of credits that you have, not the number of years you've been in high school. I suppose there are some people who have been here for 2 years and they do not have the credits to be a sophomore, but we'll call them a freshman in guidance. So freshman or a sophomore, you're one or the other. You have the credits to be a sophomore or you don't. And then a female or a sophomore, well, you could be both. I'm sure I have some of you in this room right now. Right? That's an overlapping event. Yeah. Represent. Good job, female sophomore.
I was going to say woo, and then I remembered that I'm not a sophomore.
Oh, sorry.
Oh, no. I think you can say woo.
You once were a female sophomore. Okay, and the last thing for those two columns is the information about overlaps. Disjoint or mutually exclusive have no overlaps. Overlapping have overlaps. And then I wrote something down about the probability of A and B, and that's really important, so include that in your notes. Add to this right here. Okay, now think about those two probability statements I have at the bottom and why they make sense. So if we're talking about disjoint or mutually exclusive events, they are events that cannot be both at the same time, not possible. Therefore, the probability of A and B occurring at the same time should be equal to 0. That's the worst probability there is. You should never give me a negative probability answer, right? Okay, that doesn't make sense. 0 is as low as it gets. Versus overlapping events, they could be both at the same time. Maybe they're both, maybe they're one or the other. We don't know. Okay, could be both. So their overlap does exist. The probability of A and B occurring at the same time is something greater than 0 because it's not impossible. So it is possible in some respect. Now, I should maybe also put on there that while it's greater than 0, it still has to be less than what value? 1, because you shouldn't also ever be answering a probability with a number greater than 1 or 100%. so just remember that. Okay, let's do our formulas. Now, the nice thing about the compound events is you really only have to memorize one formula, and that's the first one we're going to write down. So if you want to star, circle, highlight, box, bubble, whatever you like to do, just be like, pay attention to this. That would be for the first formula that I'm going to put up here on the board, because it's the any compound event. So any compound event would include disjoint or overlapping. This will always work. And it looks like this. The probability of A or B is equal to the probability of A plus the probability of B. Remember, or means add. But one tiny issue there, if there is overlap, you'll have counted something more than once. So you have to subtract overlap. Okay, so I'm going to say add and subtract overlap. Okay, so we'll do just like a real quick example here in class what I mean by that. Raise your hand if you are a female. I got 1, 2, 3, 4, 5, 6, 9, 11. Okay, I got 11. So the probability of being a female in this room is 11 out of 18. Raise your hand if you are a sophomore. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so the probability of being female was 11 out of 20. Plus the probability of being a sophomore was 13 out of 20. If I add those, 11 plus 13, 24 out of 20, which doesn't make sense. And the problem was, some people raised their hands 2 times. So I counted them twice. Who raised their hand 2 times? Okay, so like Lexi raises her hand 2 times. Okay. I counted Lexi twice, but there's only one Lexi that exists. So I have to subtract all those people I counted twice. Let's say there were, 7 of you. Okay, let's say I subtract them. Then I had 11 plus 13 was 24 minus 7. That brings me down to 17 out of 20, which is a much more reasonable part. And then if I subtract that overlap for like the 7 people who were female and sophomores at the same time, then I'll have counted them only once, because I subtracted the time I double counted them. Does that make sense? Now, I have a second formula up here for disjoint only, because it's a simpler formula. What do you know about disjoint events? There is no overlap, therefore their probability could just be written as probability of A plus probability of B. Done. Now, technically there's a minus 0 right there because their probability of overlap is 0 if they cannot occur at the same time. So I don't care if you memorize both of them. I would really stress the top one there, and don't forget whenever you're adding probabilities to check if you need to subtract any overlaps. Okay, that would be huge. Okay, let's look at some examples. Let's do a card randomly drawn from a 52 card deck. Find the probability of selecting a face or a black card. So I'm going to kind of go back to at the beginning of the chapter when we introduced probability notation. This is our notes, so I want to make sure everybody's clear when they look at their notes where things came from. We could write this as the probability, set it up, of getting a face, today, or a black card. Keyword is or. So we want to do the probability of a face card plus the probability of a black card minus the probability of a face and a black card at the same time. Okay, so card people, help me out. How many face cards
You're gonna have 16.
are in that deck? 12 out of 52. You have
What?
the Jack, Queen, King,
Right.
There's 4 suits.
Oh,
clubs, diamonds, spades, and
But
hearts.
isn't the ace also a face
No,
card?
it has no face on it.
What is that? You thought ace was a face?
The face cards are the ones that have the little faces. That's Jack and the Queen and the King. Now you might be playing with like kitten cards or something like that. Maybe they have faces on emoji cards. Maybe they all have faces on them. Okay, how many cards are black? 26 out of 52. Half of them. Excellent. Now I'm not gonna use like the half or the 1/4 for like colors or suits here. Only because if I don't simplify my probabilities, you'll notice all of them will have the same denominator, which will be awesome later. And then, are there any cards that are face cards and black cards at the same time?
Yes.
How many? 6. Half of the face cards are red and half the face cards are black. That would be 6.
So, if you took
them out before you did black cards, you'd essentially be doing this formula. Is that what you're gonna ask me?
Well, like, yeah, if we like simplified that to like 1/2, isn't it just like?
Yes, you could do that. Then you'd use a calculator, but I can now just do what? Add and subtract in the numerators. So I'm going to get what? 38 minus 6 is 32 over 52. And then I could divide each of those by 4, so that's 8 over 13. And you could do decimal if you wanted to. I'm just trying to make it easy on the board, so I'm not spending a lot of time calculating.
Well, right. I was just saying that, like because if you were thinking about it, like, even if that wasn't 1/2 of it, was like 1/4 of it,
Mm-hmm.
and then we used like half of that one. Does that only work for this situation? Because it's 6 is half of 12, is what I was
Yeah,
saying.
yeah, oh yeah, that works for this. Yeah, for like
So it
face
was like
cards,
the
half of them
simplified-
are red and half of them are black. But you should use 6 out of 52, not half. I'm confused by your question.
Never mind. I'll just see on my own if it works out. But
Can you give me another example besides face and black cards?
yeah, like if we were doing, I don't know, anything.
Okay.
I was just saying that.
If
Like-
you're doing a color, yes. If one of them is a color, you can always half the other group because the colors are split in half.
Right.
Yes. I agree. So if you use queens and red cards, then it would be half the queens.
Right.
Yes. Or, but not suits because suits are all one
Yes.
color. So it would depend, I suppose. Okay, let's do example 2. In a survey of 200 pet owners, la-di-da-di-da, a bunch of information, right? Data. Okay, read to the problem. Of the respondents, 119 owned a dog or a reptile. What is the probability that they owned a dog and a reptile? Talk to me about key words.
Dog and reptile.
And
overlap.
Okay, there is an and. Okay, now you'll have to be careful here. Does this and mean and then, or at the same time? This one means at the same time. What's the probability they owned a dog and a reptile? We want to know who owned them at the same time. They had both pets, right? Okay, so this is an at the same time. What's the other keyword in this problem? There is an or. So just because I'm not asking the question, what is the probability of A or B, doesn't mean that I can't use that formula, right? So I would write this out. I'm going to use D for dog and R for reptile. The probability of a dog or a reptile should be equal to the probability of a dog plus the probability of a reptile minus the probability of a dog and a reptile. You okay with that?
Mm-hmm.
Fill in the ones you know. So help me out. What probabilities can we put into the equation?
Dog for reptile.
Dogs. Someone said dogs is 103 over 200. Logan says we know dog or reptile is 119 over 200. Do we know anything else?
18 reptiles.
18 over 200 for the probability of owning a reptile. So we don't know the probability of a dog and a reptile because, of course, that's the question, right? Can you figure out what that probability is?
Yeah.
Oh, look, I got
Isn't it
dogs.
just like doing algebra?
Yeah, you could add the two. So this is really 119 over 200 equals, what is this, 121 over 200? Minus the probability of DNR. So can you tell me what the probability of DNR is? Two over 200, which we should simplify 1 over 100. Is that it? You could go further with like algebraic solving. Like you could subtract 121 over 200 to the other side. That would give me negative 2 over 200 equals the negative probability, and then divide by negative 1, and I would get positive 2 over 200. But I'm guessing most of you, because you have common denominators right here, can figure out what the probability had to be to go from 121 to 119. Must have been 2. Does that make sense? Okay. So again, remember, just because I say in my question what's the probability of A and B doesn't necessarily mean it's a multiply problem. It still could be add and subtract overlap because that A and B could be the overlap. Okay? All right. I want to make sure I get to number 4. So I'm going to skip number 3. Number 3, if you read through it, you'll probably be okay. It's just add and subtract.
So did you just exclude the 88 cats since it wasn't asked in the second part of the
Yeah,
question?
it had nothing to do with dogs or reptiles.
Right.
So I didn't need that information.
Yeah.
It is part of, I suppose, the total pet owners, but I did tell you how many pet owners there were. Okay, now just take a quick minute to kind of skim over number 4 for me on your own. No, I'm going to do it with you, but I just want you to read it. Okay, I hope what you notice in a question like 4 and also 5, there's a lot there, right?
Yeah.
So these are examples where now we've done 4 sections of probability. We could start putting it all together all at once. Okay? So tell me, when you read number 4, what are some things that are happening that have probabilities or that we could find probabilities of?
Coin toss.
There is a coin toss, right? So something has to happen with the coin toss. What does a coin toss do for us in this example? Figures out who starts with the ball. And that's really important to know because then our other probabilities depend on if you started with the ball or not. So they're dependent probabilities. So I'm going to make a tree diagram. And you guys told me one of the first things that's going to happen, there's going to be a coin toss, right? And the coin toss, Quinn said, is I start with the ball or I don't start with the ball. So I'm just going to say no down there, right? Well, I'll say no to start. And on the branches, label the probabilities. So what's the probability I start with the ball? 0.5. What's the probability I don't? Okay. So those are going to be the first branches of the tree diagram. Now the other probabilities, like I said before, they depend on this coin toss, whether or not I start with the ball. So you're going to build branches off of whether you're starting with the ball or you're not starting with the ball. So what are the other things that you know probabilities for? Whether you if you start with the ball, you can score first Liam is saying 75% of the time. What's the other option when you start with the ball?
Don't score.
You don't score first. And what would your probability be? 0.25. Josh, can you tell us how you got that?
1 minus 0.75.
Yeah, compliment. If you do score first when you start with the ball 75% of the time, you don't score first 25% of the time. Okay. And then we also have options for if we don't start with the ball, right? If we don't start with the ball, we technically might be able to score first. It will depend on whether or not the other team scores. Or we may not score first if the other team scores. So then put in your probabilities there. What's the probability that you do score first if you don't start with the ball? 49. Thank you, Lexi. That's the compliment, right? And then you don't score first? 0.51. That's the one they gave you. So you gotta be really careful when you read those problems and make sure you're putting probabilities, assigning them to the correct branches. But the best thing you can do is try to piece it apart. What are the different things that are happening that you can do probabilities of? Now we want to answer the question finally that is posed here. What's the probability that you score a touchdown first? Okay, so I'm going to say the probability that you score first. You can score first two ways. You can score first when you get the ball first, or you can score first when you don't get the ball first. Okay. So on the branches, you're going to be multiplying, and in between, you're going to be adding. Because it's like, I have the ball first, or I don't have the ball first. So that's an or. Okay. So follow the branch. Probability you get the ball first, 0.5. Probability you score, 0.75. So that's going to be 0.5 times 0.75. So that's the probability that I score first when I win the coin toss. Make sure you're paying attention. I feel like I'm repeating myself because people aren't listening. Or, so I'm adding, I could score first when I don't have the ball first. So follow that path. 50% times 49%. So 0.5 times 0.49. And all I have to do is type that into my calculator. So I'm using my ands with or. So I have multiplication and addition in the same problem. I think this comes out if you calculate it to like 0.625. Okay, so over half the time we'll score first. You don't have to worry about overlap there because there's no way for you to start with the ball and not start with the ball at the same time. You either start with the ball or you don't, and they're disjoint. Okay? So you can kind of be on the lookout for those in your homework because there's going to be lots of probabilities in the same problem. The easiest thing you can do is make a tree diagram, and there's, I think, an example also in the textbook if you want to look back for another example if you need some help with that. Your homework assignments on the gold sheet. I'll share answers with you tomorrow at the beginning of class.